All right. So let's start the discussion on this topic. All right. So, what are intrinsic and extrinsic semiconductors? How do you decide what is the meaning of these words, etc.? I'll just paste something for you so that you have a reference point. Okay. Okay. So tell me, what are semiconductors? What are they? What is a semiconductor? We studied in the previous class.
For semiconductors,
You're right.
Okay,
Say it. You're right.
they are between metals and insulators.
Then electrical conductivity
Like
is
the
between
forbidden gap in semiconductors is in the middle. In insulators,
0.7.
it is more than semiconductors, and in metals, there's no forbidden gap.
In insulator, it is more than semiconductor. In metal, there's overlap.
It's overlap. No.
Okay. Right. So let's see what are semiconductors. Okay. So these are the materials that have electrical conductivity, which is between conductor and insulator. Now,
What is the perfect definition for what are semiconductor materials with electrical conductivity between? Okay.
Yeah.
Okay, understood.
But now semiconductors have special property that you can change the conductivity of a semiconductor by few things. One, by temperature. Second, by using impurities. By adding impurities, the word in semiconductor for that is doping. Okay?
Doping, okay.
That is the word used for when you mix impurity with a semiconductor material. Okay? Now, there are two types of semiconductors which are there based on their purity and the presence of impurity. So there you will see two types of semiconductors based on their purity and presence of impurity, both. Okay. So what they're going to do is they will change the conductivity not by temperature. We don't need to worry about it right now. We just need to worry about the doping part of semiconductors. Okay. First of all, let us understand what is an intrinsic semiconductor. Okay. So what is a Something went wrong. So intrinsic semiconductors are pure semiconductors. They have no impurity in them.
Okay.
Intrinsic. They have no impurity in them. And by the similar logic, the semiconductors which have impurity present in them means they are doped. You change their conductivity.
Listen, what did you tell about dope? Intrinsic are the pure semiconductor.
Addition of impurity. So extrinsic semiconductors are doped.
Okay.
Intrinsic are pure. If you add impurity to intrinsic, it will become extrinsic.
If you add impurities to intrinsic, it will become extrinsic. Okay.
Right. Now, what does it mean to be pure? What does it mean to be impure and stuff like that, right? So let's see the definitions. and what are the key features of first intrinsic semiconductors, and teach some details of them. Okay. It is very common sense driven, but now you will see why I'm saying that. Okay, so let's see. An intrinsic semiconductor is a pure semiconductor without any significant impurity, right? The electrical properties of conductivity, which is purely decided by the material it is made up of. For example, in semiconductor industry, the two famous elements are silicon and germanium. Right? We say Silicon Valley. Bangalore is Silicon Valley. Why? Because it is chip driven.
Okay.
The chips are made up of silicons.
Okay.
If you use only
So like
silicon
the
or germanium,
chips are intrinsic semiconductor.
can be both. Basically, they are made up of either of these two. But the electrical conductivity is poor with pure. So to improve the conductivity, we do addition of impurity. That is, we dope silicon and germanium to convert these into extrinsic semiconductors so that the conductivity goes up. If you use a pure semiconductor, the conductivity is not good.
Okay. So matlab extrinsic are more conductive in nature.
Yes. More electrical conductivity.
But silicon and germanium can also be considered as intrinsic now.
They are intrinsic.
Okay. They can be converted to extrinsic by doping.
Addition of impurity,
Okay.
which is doping. So they are made up of pure material. The charge carriers in these remain electron, which are in the conduction band. And the second type of charge carrier in semiconductor, which is new to you, is a hole. Okay? So in semiconductors, unlike electrons, which have only electrons for the purpose of conduction, you also have one more thing called as a hole.
In the valence band.
Right? So both are available in equal quantities.
Okay.
A hole generally is considered to be a positive, not negative. Electron is negative. Both of these, electrons and holes, contribute to electrical conductivity of a semiconductor. But in a metal, only electrons contribute to the electrical conductivity, not in the case of semiconductors.
In semiconductors, both, and in metal.
Allow me to complete the sentence and then speak. Don't speak over me.
Okay.
Wait. So holes are considered positive. I will tell you what are holes in detail also. Right now, we are studying at a high level the varieties and what all happens in them. Now say.
I was just saying that only electrons are considered in the metals, and electrons and holes are considered both in the semiconductors.
Responsible for the electrical conductivity property of these.
Okay.
Metal and semiconductor respectively.
Okay.
Now, the number of charge carriers, how many electrons the semiconductor will have in the conduction band, how many holes will the semiconductor will have in the valence band, purely depends on temperature. If you have higher temperature, the electrons will jump into the conduction band. And when they jump to the conduction band from the valence band, what they leave behind are holes in the valence band. The vacancy, which is created when the electron leaves the valence band and jumps to the conduction band because of increase in temperature, is called as the creation of that vacancy is called as a hole. Nothing is there.
Okay.
The electron leaves the valence band and crosses the forbidden gap and reaches the conduction band. What it leaves behind in this process is a vacancy called as a hole. but it is the holes are in valence band, which is where the electrons came from into the conduction band.
Okay.
If you have 10 electrons jumping from the valence band to the conduction band, you will have 10 holes left by those 10 electrons.
Okay.
Right? So temperature will have an impact on the conductivity, because higher temperature means more electrons jump into the conduction band and leave behind equal number of holes. So higher temperature means more conductivity.
Okay.
Okay. Second point. Electrical conductivity. Now, the intrinsic semiconductors, which are pure semiconductors, have poor conductivity at room temperature, as they don't have much thermally generated charge carriers, which is electrons jumping from valence band to conduction. So low temperature, they're useless. But if you increase the temperature of the room or the environment, you see a small change in the conductivity of the intrinsic semiconductors, because you find that a lot of electrons few electrons are able to jump from the valence band to the conduction band, and in the process they leave behind holes in the valence band. What is an example of intrinsic semiconductor? Silicon. Other example is germanium. Let's go to the extrinsic semiconductor. What is an extrinsic semiconductor? And similarly, how do we study the impurity aspects of semiconductor, this type of semiconductor, which is impure in nature? And this has been made impure deliberately, because intrinsic semiconductors are not useful in the industry. The electrical conductivity is so poor that you actually cannot use it to make anything. You have to have doping.
Okay.
So doping is more popular way of using a semiconductor. So extrinsic semiconductors are used in the industry, not intrinsic. They're good for nothing. Now, how do we dope and all that? We will not study that. This is not engineering. What we will study is the definition, theory of extrinsic semiconductors for CBSE only. All right. So an extrinsic semiconductor has been intentionally made impure. Why? To modify its electrical property.
Okay.
What happens? Why the electrical property changes? Because the impurity brings a wealth of additional charge carriers. The more are the charge carriers, better conductor you become.
Okay.
Right. Second, what are the key features of extrinsic semiconductor? Obviously, you do doping of an intrinsic semiconductor and convert it to an extrinsic, right? But how you do it? You actually use controlled amount of impurity. You cannot keep on adding impurity believing the conductivity will keep on increasing. It does not. There is a ratio. Specific amount, controlled amount is there. Only then the intrinsic semiconductor will exhibit improvement in conductivity. Otherwise, when the current comes, these chips will not work. They will not, because you have done wrong doping. So doping has to be done carefully. There is a standard value. We don't need to study that. It is a practical engineering topic. But you should know. Now, what type of material is used for creating this impurity? The first material is the donor impurity. What does it do? It is capable of giving extra charge carriers by giving you more electrons.
Okay.
And these electrons straight away are available in the conduction band.
Okay.
So they have no dependency on the temperature. What are the examples of a donor impurity which gives you extra electrons? Phosphorus and arsenic.
Okay.
What second type of impurity that you add is called as an acceptor impurity.
Okay.
These what are they capable of? They give you additional charge carriers called as holes. And the two examples of acceptor impurities are boron and gallium.
Okay.
So these questions will come in the board examination. Give two examples of acceptor impurities. What value do acceptor impurities bring? They create holes, more holes.
Okay.
Than were available in the intrinsic semiconductor.
Yes.
Let's talk about the next property of the extrinsic semiconductor. So one is they are doped in two ways using two types of donors, the donor impurity and the acceptor impurities. Two types of dopants, donor, acceptor.
Okay.
Second property is the charge carriers. Okay. If you have more electrons, you can have either of the situations. So if you add acceptor impurity, the intrinsic semiconductor will have more holes than electrons. If you add a donor impurity, the new semiconductor
will have
more electrons as compared to the holes.
Okay.
So you can add either, okay, and decide which one do you want. You want more electrons or more holes.
Holes.
So we can say there is a. So
what is the difference between the holes? Does that holes are in the valence shell and electrons in the conduction?
Valence band.
Band, sorry.
Yeah, and the electrons are in the conduction band.
Okay.
If you're asking me where do they reside in the band theory, so the electrons that contribute towards electrical conductivity have to jump from valence band, which is a band of energies in which valence electrons are there, and then there is a forbidden gap, and then there is a conduction band. So the electrons have to be in conduction bands for them to be participating in conduction of current. And holes have to be in the valence band for them to contribute in flow of current.
Okay.
Right? All right. Now, who will be, so if you have more holes or more electrons, we label them as majority carrier charge. So you can have a majority of electrons, then the majority charge carrier is electron. If you have majority of holes, then it's a majorly a hole-driven conduction, right? Holes have more power of conduction there. They increase the conductivity of the intrinsic semiconductor. All right. Now, depending on the type of majority charge carrier you utilized, you will get two types of extrinsic semiconductors.
Okay.
Within extrinsic semiconductors, which are impure, made impure by the donor impurity or the acceptor impurity, you will have two categories based on who's the major charge carrier now, okay? The first one is called as N-type semiconductor, created with the help of phosphorus and arsenic. Okay? The N-type semiconductor has more electrons. Who provided the extra electrons? The donor impurity. We call them N-type, negative type semiconductors.
Okay.
More negative charge carriers.
So they are doped with donor impurities.
Yes.
Okay.
And by the way, phosphoric and arsenic are pentavalent. They can lose one electron. 5 electrons are in the external shell, and the last electron can be given away to the intrinsic semiconductor to make it impure. So the extra electrons which are coming from these donor impurities.
Can you repeat the last time a second?
If you use arsenic and phosphorus, they can provide extra electron in the conduction band straight away.
Okay.
Resulting in formation of an N-type semiconductor.
Okay.
If you have acceptor impurities, okay, they have they are electron deficient.
Hmm.
They have more holes. I will show you how they look and appear and all that, right? But point is, if you use acceptor impurity, you will end up creating
P-type.
a P-type semiconductor. Right? Why did we do all of this? For the simple reason, we want more electrical conductivity.
Okay.
We want more. So why was doping done? To improve the electrical conductivity. What are the examples? Silicon doped with phosphorus is a
Example of electrical conductivity
improvement, but
of
the
N-type.
semiconductor that got created is called as N-type.
Hmm.
If silicon is, which is pure semiconductor, is made impure by addition of boron, then you're going to create P-type semiconductor, which means you will have more holes in the valence band. Generally, silicon itself has holes, which is equal to the number of electrons it has, but electrical
Yes.
conductivity is pathetic.
Okay.
If you provide extra holes, you will create a P-type. If you provide a source of extra electrons, such as phosphorus and arsenic, you will create a N-type semiconductor.
Okay.
Now, how will the question look like in the exam? Let's see. They will ask you, what are the differences between the extrinsic and intrinsic semiconductors? You have to memorize all of this. Study and tell me which point is not clear to you.
Yeah.
Read it.
Understood.
You don't have to go do a PhD in this, okay? Just remember. So this level of detail is what board requires you to know. Okay.
Thank
Now
you.
let's get into understanding how does this, what is arsenic going to do? I've already told you what arsenic will do. It will give away extra electron, right?
Yes.
Right. But what exactly happens? Okay. Slight amount of detail now.
Yeah. Arsenic comes in the donor impurity.
N-type. So what exactly is, okay, general statement is it plays a very crucial role because it is a donor impurity. It will give you extra electron and pure semiconductors like silicon and germanium will become N, right? But let's study more about the doping with the help of arsenic, okay? Let's study.
Okay.
So that you get more sense and more understanding of what, and this is part of our syllabus. You have to know all of this. What is the role of arsenic is not limited to one statement that it gives you extra electrons. There is more to it. Okay. Arsenic has some qualities. Now, what
Okay.
are the qualities? Now, arsenic plays a very important role in creation of N-type. We already know this. We also know that it is a donor impurity.
Yeah.
Now, let's talk. So, I told you arsenic and phosphorus both are pentavalent elements. They have 5 valence electrons. But the pure semiconductors like silicon only have 4 electrons. Valence electrons. If you write the electronic configuration of silicon and germanium,
Yeah.
812, 84, stuff like that, you will find that silicon and germanium both have a tetravalent. They have 4 valence electrons outside.
Okay.
when you add arsenic to the silicon crystal, sorry,
doped with.
when you add the arsenic atom to the pure silicon,
Yeah.
silicon is available in the form of crystal lattice.
Okay.
Some silicon atoms are removed and replaced by the
Silicon.
arsenic atom. So for every one replacement arsenic does, what happens? So 4 of the arsenic's valence electrons forms bonds with the surrounding silicon atom, because silicon is tetravalent, and you have lost one silicon to arsenic. Arsenic is pentavalent. 4 covalent bonds get created between one arsenic and one silicon. So silicon has exhausted all its 4 electrons because it is tetravalent, and arsenic has lost 4 electrons to the covalent bond and is left with 1 extra electron because it is pentavalent.
Okay.
Silicon is tetra. Arsenic is penta. Arsenic replaces silicon.
Okay.
And bonds with the neighboring silicon. Or out of 5 electrons which arsenic has, 4 get utilized in forming 4 covalent bonds with the neighboring silicon atoms.
So only one bond is left.
One is left. That is an extra electron you got. So this electron is now available loosely inside the crystal lattice.
Okay.
If you apply voltage, which is current, battery,
yes,
this electron is available to you because electric field has come. It will contribute in flow of electricity.
Okay, so the one electron which is left will contribute in electricity.
Yes. So you've got a bonus, right? By replacing one silicon, you got 1 extra electron.
Yeah.
If you replace one
arsenic with silicon.
Yes, yes. Say that again. What did you want to say something?
No, I was saying ki arsenic, like when we replace arsenic from silicon, then it's a benefit. Like 1 electron is left.
You replace silicon with arsenic. You replace silicon, some of the silicon atoms with the arsenic atom, which is pentavalent, and get for every replacement 1 electron extra comes to you, available for conduction.
Okay.
And this electron is loose because it cannot bond with anyone, because silicon is tetravalent.
Okay, sir.
Got it?
Yes, got it.
Okay. Let's move forward. Now we know we have extra electron, and that is why the majority carrier is electrons. It is more than the number of holes now. A pure semiconductor has equal number of holes and electrons, because the electrons that jump from the valence band to conduction band leave a hole also. So the number is equal. But the moment you make it impure, you have more electrons in the case of N-type. Okay. Now,
more in the case of
N-type, negative.
N-type, yeah, okay.
More electrons, more negative. Okay. Now, so the presence of these free electrons increases the number of negative charge carriers in the material. Since the material is now majorly having electrons, what type of semiconductor do you get? An N-type of semiconductor, right? The arsenic atom, after donating the extra electron, itself becomes positively charged ion, but remains fixed in the crystal lattice because it is bonded to the neighboring 4 silicon atoms. But itself it becomes a positively charged ion. Obviously, if you lose an electron, you will become positively charged.
Yes.
Now let's come to what is happening at the energy level for these extra electrons. Okay. Now your donated electron, and this is the trick actually. Trick is not just giving an electron. Trick is give an electron which is very close to your conduction band. So that it is very easy for this electron which is donated by the arsenic atom to jump into conduction band. So its energy level is slightly below the energy level of the conduction band of the
silicon.
yeah. It has come as an outsider.
Okay.
Electron has come as an outsider. It has been donated to it. It has come from arsenic. But there is a special property of this electron. Its energy level is very close to the energy level of the conduction band of the silicon. Otherwise, all the electrons which are in the conduction band actually came from the silicon itself by jumping using temperature. But their forbidden gap was very high.
Okay.
So higher temperature was required for any movement. But if the gap is very small, that is an outsider comes whose level of energy is already almost as good as conduction band, then you don't need much of temperature for this jumping.
Yes.
So even at a room temperature, the moment you do doping, what you find is suddenly the current increases because the donor electrons are at slight and lower energy as compared to the conduction band energy of silicon.
Okay.
So the distance you need to travel or the energy you need to move from that almost closed level is negligible. It is available to you at room temperature.
Okay.
And you can't increase the temperature infinitely to make intrinsic semiconductor to work for you because more temperature can destroy it.
Yeah.
You can't pick up a pure semiconductor and say, I will not use impurity. I will increase the temperature. All electrons will jump into conduction band. You can't do that. If you
Yes.
heat it too much, it will get destroyed.
Okay.
How do you work at the room temperature then without depending on temperature? Introduce an impurity which has little gap, forbidden gap, compared to the silicon forbidden gap. So silicon electron jumps this much, 0.7 electron volts, and needs a lot of temperature for jumping from valence band to conduction band. But you are arsenic electron. The electron of silicon has to jump from first floor to eighth floor. The arsenic electron is already available at 7.5 floor. To reach 8th floor, it has very little gap.
Yes.
Karo,
Nice. Okay.
Got it?
Yes.
Makes sense? Common sense. No, this is no physics. This is common sense.
Yeah.
If somebody donates money to you, you will become positively rich. If somebody takes away money from you, your books will show negative balance.
Yeah.
You become negative, right? So as simple as that. So common sense. So energy levels of the donor electron is also very important. Just by saying I will donate an electron and I will get an N-type semiconductor is wrong. I will give donation of electron to you, but I guarantee that the level of energy it has is slightly lower than your conduction band. So I need very little thermal energy for me to jump from my energy level of the donor electron to your silicon, your conduction band.
Okay. So just give me 5 minutes, just a minute.
Okay.
Yes.
All right. Could we move forward? This point is clear?
Yeah.
All right. So we will just recap this. Arsenic is used as a dopant because it is capable of giving you extra electron. Yes.
Yeah.
So you need a pentavalent. Otherwise, you won't get the extra.
That one electron can be used in the conductive
Yes. It converts silicon into N-type. It does because major carriers become electrons.
And then it becomes positively charged after giving the
Ion.
ions. Yeah.
The resulting material has improved conductivity as compared to the undoped silicon, making it useful in devices.
Okay.
Got it?
Yes. So, like, just wanted to ask, like, just say silicon is doped because to like make the devices these like more helpful in those devices.
Right.
Okay.
Because it has better conductivity.
But like before doping, it doesn't have that much better conductivity too.
And also this conductivity is provided at room temperature.
Okay.
You don't need any. I'm a user of mobile phone. My mobile phone has a lot of semiconductor devices inside it and integrated circuits. Will I go to my microwave oven to use my mobile phone to heat it up? No.
No.
So I need conductivity at low temperatures, at room temperature. How do I get it? Without heating my equipment. Doping.
Yeah.
That's the beauty of doping. It reduces your dependence on temperature. It increases your conductivity without depending too much on temperature.
Yes.
Now let's study the same thing. What does boron, for example, do in making a p-type semiconductor, which is a positive?
Yes.
All right. So now we're going to dope or mix boron. You can add the other one also, the example I gave you, right? I gave you two examples. One was boron and there was another one, which are used to create p-type semiconductors.
Yes.
Boron only. The theory is applicable to both.
Yes. Okay.
Okay. Let's study the boron now. What happens when you add?
Boron and phosphorus.
No. Phosphorus and arsenic are N-type.
Okay.
Right. Boron and one more. Okay. So boron, right? Boron is basically what type of impurity?
Acceptor.
Impurity.
Yes.
Okay. And if you introduce it inside a pure semiconductor like silicon and germanium, you are able to provide a lot of holes in the valence band, close to the valence band or in the valence band. So your conductivity goes up because of large number of holes now. And you become positive, P for positive. P-type extrinsic semiconductor gets created. How? What is the mechanism? Boron is trivalent. It is not pentavalent, it is trivalent. So it has 3 valence electrons, but silicon and germanium have
tetra,
4. So which means 3 boron electrons can only bond with 3 silicon electrons. Right?
Yes.
So obviously they will replace some silicon atoms from their position. That is a process of doping. How they do it, more of engineering. They do it, however, some way. The moment you add the extra, these boron atoms, they remove silicon from their position, come in place of silicon, but they are only trivalent. So they can only bond with 3. So that means they can't bond with all 4. Now what happens? We say that boron therefore is an electron deficient atom. Why? Because it lacks one electron to form the fourth covalent bond.
Covalent bond with
Cannot
silicon.
create. Right?
Yes.
The missing electron in the world of semiconductor is called a hole.
It's called a
Hole.
hole. Acha, okay.
If you find that an atom is inside the lattice, but has less valency than the silicon, 3, not 4. Boron has 3 valency, right? Trivalent. It will bond with 3, but we will say it's an electron deficient. The moment the word electron deficient comes, what we mean is a hole only. Because you're electron deficient.
Yes, sorry.
Because you're electron deficient, therefore you are positive. If you are electron rich, you are negative. Right? Anything which loses electrons becomes a cation, positive ion. Similarly, in the case of holes and electrons, something which lacks, if something has excessive electrons, good, N-type. If you have less number of electrons and you have come and replaced silicon, but not sufficient electrons to bond with all 4 and bond with only 3, we will say you're hole rich.
Okay.
It sounds very absurd, somebody telling that you are rich because you have less money. It sounds very strange, right?
Yeah.
You are rich in holes because you have less electrons.
You are rich in holes because you have less electrons. Yeah.
You have a missing electron, not less, you have a missing electron. You become rich in holes if you have missing electrons. Okay? Yeah. So the missing electron concept in this world, not metals, is called as a hole, and a hole is treated as a
like positive
charge carrier. Just reverse of N-type.
Yes,
N-type, the extra electron is treated as a negative charge carrier. In the world of semiconductor, we will treat this as a positive charge. Electron missing. Electron missing, we say in the world of semiconductor, results in creation of a hole.
Understood.
Like electrons move in the conduction band, holes move in the valence band. Actually, holes will not move. What happens is the electron comes from the neighboring atom and leaves the hole behind.
Okay.
And the next electron comes and occupies the hole and leaves behind a hole. So it appears to you that the hole is moving. The hole is not moving. The hole is getting created because electron is jumping to the hole, leaving behind a hole.
Okay.
Right? So there are electrons also in that world, which are there. These electrons keep on jumping. And whenever they jump, they leave behind a hole. So if this jumping, one electron keeps on jumping 10 places, you will say the hole is here. The electron jumps, the hole is here. The electron jumps, hole is here. It will appear to you that it is the hole which is moving. In fact, the electron is jumping, but leaving behind hole. But the hole is getting left like this.
Yes.
So it appears that the hole is moving. So it is very, very, very theoretical concept that hole is moving. Right? Yeah. So moving of the hole is actually nothing but the electron, the hole, accepts the electrons from a neighboring bond.
Yes.
It has already 3 bonds, right?
Yes.
It may accept an electron from a neighboring bond. It may share that bond. So the hole will not be there. But the moment someone gives away the electron to them for creation of bond, the electron appears there.
The hole is left.
On and on and on it happens. So therefore we say holes are moving. But actually holes never move. It is the electron which is moving, resulting in creation of a hole that gives an impression of hole moving.
So what we'll write in exam, the hole is moving or the hole is left behind?
You can write moving.
Achha, okay.
If they said, does it really move? No, it effectively moves.
Okay.
Because to the eyes, it appears moving. But does it really move? No.
No.
The movement is of the electron.
Okay.
Which is coming from neighboring atoms to fill the hole and leaving behind hole there.
Yeah.
The hole was visible here, now the hole is visible there. So effectively, you can say, for the purpose of ease, that this hole which was here has moved there. It has not moved. It has been filled up and now a vacancy has been created there.
Yes.
Right? In reality, no movement is there, but effectively movement is there. To the eye, it appears to be moving. Let's move forward. All right. So now you understand what is a P type, right? It's a acceptor impurity.
Yes.
Okay. P type semiconductor formation. The introduction of boron increases the number of holes in the material.
Yeah.
Since holes are majority charge carriers, the material becomes a P type semiconductor. Positive.
Yeah.
Why are they called acceptor type of impurities? Because that boron starts accepting electrons from the neighboring atoms, resulting in something like movement of hole.
Okay.
It's an acceptor of electrons. It is not accepting holes.
Yes.
Because it accepts electrons, holes appear.
Okay.
And because it accepts the electrons from neighbors, which are silicon, it becomes
negatively charged.
But the one who gave away its electron, there the hole gets created. Because after all, the neighbors are also what? The neighbor is also tetravalent, right?
Yes.
They lose one electron missing, hole.
Okay.
Right? So why are they called acceptor impurities? Because they accept electrons, resulting in creation of hole somewhere else.
Yes.
And in the process, they become negatively charged ion because they accept the extra electron. They are supposed to be trivalent. If a trivalent atom accepts the extra electron, it will become positive. It will become negative. If you are 5 pentavalent, you lose electron, you will become positive. Arsenic becomes positive.
Okay.
It donates electrons. This guy accepts electrons.
Understood.
Okay. Now, so somebody said, okay, so that means if I create holes, will conduction start? No. You also need to be aware of the energy level. So what do you mean? Like if you are in first floor to 8th floor, or you come as an electron at 7.5 floor, which has to move to 8th floor. Easy. Like we studied in the previous example. Similarly, here also, the energy level, right? Which is associated with the hole, not electron here, because we are treating hole as a charge carrier. The energy level associated with the hole should be close to the valence band of silicon. They should be close. So they should fall down inside the silicon valence band because holes conduct electricity when they are in the valence band, not in the conduction band. Electrons should be in conduction band for them to participate in electricity flow. Holes have to be in the valence band. So the electron, which is the hole which gets created, should also be close to the valence band of silicon. Otherwise, it will not contribute. If the hole comes in, extra hole is created, but the energy level is much above the valence band of the silicon, nothing will happen. It should be very close to the valence band. It should just so close that it can, easily lose some energy and go inside the valence band of the silicon.
Okay.
So for this, we don't need to do anything. It can happen at room temperatures.
Okay.
So even P-type semiconductors are very successful in giving conductivity at room temperatures. You don't need to do anything extra for this hole to go inside the valence band. You don't need any source. Room temperature is enough.
Yes, okay.
Right? So at the room temperature, the electrons from the valence band, right? Sorry, the holes from the valence band. Sorry, I'll just remove this. At room temperature, thermal energy is sufficient to promote electrons from the valence band into the acceptor level.
Okay.
Read it very carefully. There is a new level. One is a valence band, then there is a conduction band. But then we have introduced the new terminology, acceptor level. Right? So the electron which it accepts, boron accepts some electron, right, from neighbors. Boron accepts electrons.
Yes.
Right? What happens in that process? Holes get left out. Wherever the electron goes to the adjacent boron, it leaves behind a hole, right? So the electron which goes to the boron, because it makes the boron then negative, right? This extra electron that the boron receives, right? It should be at the energy level of the acceptor. Any Tom, Dick, Harry electron will not be able to be accepted by the boron. Boron will accept only those electrons which are at a certain energy level. These electrons at an energy level called as a
acceptor level. Yes.
So normally the electron is in valence band. It cannot, we don't want it to jump to the conduction band of silicon. We introduce an impurity. The impurity has an acceptor level. And the acceptor level means this electron coming from the neighboring band at least should move to the level of boron.
Okay.
Boron's energy level is the acceptor level. So this electron in the valence band of silicon has to be promoted to the level of the boron called as the acceptor level.
Okay.
So the context of acceptor level is not to do with hole, which I told you. It has to do with the acceptance of electrons by the boron. If boron does not accept electrons, what will happen? No holes will get created.
Yes,
right? So this promotion, but it should be close to the acceptor level should be close to the valence band. So that the promotion of the electron from the valence band of silicon to the acceptor level is very short journey.
Yeah.
So if the valence electron is at first floor, the acceptor should be at 1.5 floor.
1.5, yeah.
So easily the electron will say, I can easily go at room temperature.
Yes.
And so the acceptor level is very close to the valence band of the silicon. And in the process, it leaves behind the holes in the valence band. So there is no movement of holes in this. It's a movement of promotion of electron from the valence band of silicon to the acceptor level of the boron. And once this valence bond gets promoted and goes to the boron's acceptor level, joins boron, makes it negative. It leaves behind a hole in the valence band of silicon. And we know holes only contribute to electricity when they are available in the valence band.
Valence band, yes.
Okay, so this is the summary. Read the summary. Now I will show you the diagrams for these. The energy level diagrams, where is the acceptor level. So you have clarity. If you get multiple choice with 4 figures, then you know this acceptor level is close. So they're referring to a P type. Okay, there the donor level is close to the conduction band. So the electron can jump from the donor. Donor has to be close to the conductor. So they're talking about N-type semiconductor. From the diagram, you should be able to make up. So far, so good?
Yes.
Okay, I've tried to make it as simple as possible. Just give it a good reading, you will absorb it. I will test you on MCQs shortly, but wait. After you see the diagram, I will test you. So this topic will also get over in your mind. Let me see if I can get some good diagram for you. It's in, I think it's in NCERT also, but I don't like their diagrams. No, not impressed. All right, let's go to the.
Is it there in NCERT?
Yes, it is. It will come in paper also. They will ask you to draw the donor.
like I think which were there like before ना पिछली क्लासेस से वो थे semiconductor insulator उसके diagrams.
Look at this.
Oh, N-type.
You see, it's an N-type because it has extra electron. And this donated electron, however, the energy level is close to the conduction band of germanium. Germanium is just like silicon. See, the conduction band is very close. This is silicon's. Otherwise, all the electrons will have to jump this much, which requires a lot of temperature.
Yes.
You don't want that dependence on temperature. So you introduce an impurity which is capable of giving electrons at this level. So you only need to jump this much.
Yeah.
So this is the diagram I was referring to. So this is the lattice. This is the way you need to represent the lattice and the 4 bonds, neighboring bonds. You see arsenic has come in and replaced one germanium. and created bond number 1, bond number 2, bond number 3, bond number 4. All 4 are covalent bonds.
Okay.
And the energy diagram. They can ask you to draw an energy diagram for an energy band diagram for an N-type semiconductor. Draw this.
I need to remember this.
Yes.
Okay.
They can ask you to explain P-type semiconductor in detail. You have to draw this diagram. N-type, sorry.
Yeah, okay.
Showing arsenic, an extra electron is available, the free electron, right? But the free electron has a good thing. It is available at this energy level, so it can easily jump.
Okay.
The electrons which silicon has are available, but they're useless because they need a lot of temperature to jump. Hey, they are available at this energy level, but they're useless.
Yes.
You want things to work at room temperature.
Room temperature.
Right. Hope this is clear.
Yes.
Energy band diagram of N-type semiconductor. Different question altogether. Okay. Let's see the diagram of the P-type. Look at this. So the electron which has to leave the valence band of silicon and be accepted by boron has to be at this energy level.
Yes.
So this donor is ready to accept an electron from here. Easily it can accept.
Okay.
And in the process, this electron will leave behind these white dots. You can see the white dots?
Yeah.
Holes.
Okay.
Right. And look at this diagram, the adjacent diagram. What is the story in this diagram, right? You can see the story in this diagram.
Silicon.
The silicon has been removed by one boron. The boron has created 3 complete bonds up, left, and down.
Yes.
But look at what is happening on the right-hand side of boron. It does not have the 4th electron. Right? So what is visible is a hole because it has no 4th electron available. Now some electron will come from here and fill this space. In that process, the hole will appear to be available at the place from where the new electron has come. So you will see the hole here now.
Understood.
So you will say hole has moved from here. No. The previous hole has been filled. See, if you have a cup of tea, right? And if you add cup of tea and then remove it, right? Wherever the removal takes place, you will see emptiness, right? So empty. So pick up tea from here and fill it in the next cup.
Yeah.
What will happen to this cup? Empty.
Empty, huh?
Right? So we can't say that cups are moving.
Yeah. The tea is...
It appears as if cups are moving, but actually tea is moving.
Tea is moving.
Leaving behind empty cup. You will say empty cups are moving. They are not.
Yes, no.
The tea moves and it appears the cup is available there now.
Yeah.
Clear?
Yes.
The band diagram. Look at the gap here. As compared to the forbidden gap of 0.7, the electron has to be just promoted from silicon's valence band by how much amount? The forbidden gap has gone down so much from 0.7 to only this.
Yeah.
This is hardly any value. If nobody accepts, no holes will get created. Logically, you would like that the electrons of silicon get accepted here.
Yes.
Very difficult. Leaving behind hole, right? Not possible. So you decide I will introduce a acceptor impurity, which can accept the valence electron only very close to the valence band.
Yeah, okay. Can we keep till here only? I'm having 4 baje.
Yes, can. I hope this is getting clear in your mind.
Yes, yes, definitely.
I will make you do MCQs next time.
Yeah.
And study the next topic of PN junction.
Okay.
See you then. Bye.